Okay, something I want you guys to do. Today we're going to talk about finding roots of all polynomials. All the roots of a polynomial. And we're going to restrict ourselves to some easier problems today. But really, I want you to write this at the top of your sheet. You can write it at the top of this if you want. I suppose that would be fine. But write this down. Every polynomial can be written as that. And that's really shorthand for a larger, more complicated mathematical thought that you learn it when you take a course called abstract algebra in college. And what it really says is that a polynomial can be factored. And if we could factor every single polynomial to look like that, it would be easy to identify all the roots, wouldn't it? The problem is we run out of factoring methods. And as you notice our decision tree, we've been residing on the factoring portion here for a while, when in fact sometimes that does not work. But we always start at the top here. And I would like you to look at the first example problem that I have for you. And it says as follows. It says, find all the roots of the polynomial. Okay? You write your name on there. This is going to be your assignment. And we're going to start with the easy type of problems today. We're not going to give you any really hard ones. But we start with a very basic example. And our decision tree first tells us that we identify the number of roots of the polynomial. How many roots are there in this problem? How many solutions? There are 3. That leading degree tells us exactly how many solutions there are. There are 3 solutions. And then we go down the list, and the next thing it says is, does the polynomial factor? Does it? No, it doesn't. So now we're over on this side, and we're left to use the rational roots theorem. And here's what the rational roots theorem says. Okay, you don't have to memorize this, but here's what it says. If a rational root exists, what's a rational number? Give me an example of a rational number. 1 is rational. Give me another one. 2. How about something more interesting? 1.5, which is 3 halves. That would be an example. 0.3 repeating is 1/3. Anything that can be expressed as a fraction. So if the polynomial is a solution that can be expressed as a fraction, at least one of the solutions will be one of the p's divided by one of the q's. And if you look, it says use the rational roots theorem. And the way that we start is we identify factors of the constant, the p's, and the leading coefficient, the q's, and we write them as quotients just like so. So that's what I'm going to do next. I have this piece right here. I need to identify my p's and my q's. Now, the p's are factors of this. And the q's are factors of that. What are the factors of 6? 1, 2, 3, and 6. What are factors of the q's? Is the coefficient in front of the leading term. What are factors of 1? 1. So, as somebody summarized during second hour, they said, oh, this is kind of like a guess and check. Yes, but this is an educated guess and check. What this is doing for us is it's saying that if there's a rational solution, then one of them will be my p's divided by my q's. So I take all these and I divide it by my q's. What's 1 divided by 1? And we write it as plus or minus. It could be positive or negative for all we know. And then plus or minus 2, plus or minus 3, and plus or minus 6. So we have 4 solutions, I'm sorry, 8 possible choices there to choose from. And that's what they are. They are possible solutions. If one of these numbers is a root or a solution to the polynomial, if we plug it in, what should we get? What value should we get if we plug it in? 0. That's what it means to be a solution or a root. You will get 0. Look at the chart that I gave you. It says identify the p's and the q's and then do this. Use synthetic substitution to identify the root, which is plug in each choice till you find one that works. I like to start with the easy number. The easy number to plug in is 1, and so that's the one I'm going to use. What's 1 to the third? Minus 7 times 1 would be negative 6 minus 6 is negative 12. So that didn't work. 1 did not work. Then I moved to negative 1. I'll try negative 1. What's negative 1 to the third? Yeah, so I have negative 1, and then negative 7 times negative 1 is positive 7. Minus 6 gives me 0. So negative 1 worked. Negative 1 is one of the 3 solutions that I have. I now want to find the remaining 2. Well, think about it for a second, you guys. I told you that this could be factored, okay? Could be written in factored form. You tell me this. If negative 1 is a solution, what binomial divides evenly into that? If negative 1 is a solution, what binomial divides evenly into it? Right? Remember yesterday we were dividing things, and we found that sometimes we would divide it, we would divide evenly, sometimes it wouldn't. Well, when we plugged in negative 1 for synthetic division, if it divided evenly, we came out with a remainder of 0. It's the same way here. We know that this is one of the factors. Here's what we don't know. We don't know what the other 2 factors are. But we can find the other 2 factors by dividing the new polynomial. And here's how I do it. I take the root, which is negative 1. I write my coefficients. What are my coefficients? 1, 0, negative 7, negative 6. I drop down the first one. Negative 1 times 1 is. Add them together, I get negative 1. Negative 1 times negative 1 is 1. Add it, I get negative 6. Negative 1 times negative 6 is 6. Add, I get 0. What is my new polynomial? So, this is my new polynomial. 2 more of the solutions lie within here. I can set it equal to 0 and solve. Let's look at the decision tree, the process map, see where it leads us. It says use synthetic substitution to identify the root. We did. Negative 1 worked. Then it says divide the polynomial by the new known factor. We did that. Let's look at our resulting polynomial. Is our resulting polynomial of degree 2? Yes. So because it is, we then may solve by either factoring or using the quadratic formula. Let's try it. Does this factor? What does it factor to? So my solutions are 3, negative 2, and then my original one, which was negative 1. So if you think about it, everybody, my solution was negative 1. That means that x plus 1 was a factor. Another solution was negative 2. That means that x plus 2 was a factor. And another solution was 3. That means that x minus 3 was a factor. It turns out that this piece right here does factor to x plus 1 times x plus 2 times x minus 3. It does factor to that. Now, you don't have to use that. You don't have to know that. But I'm just telling you that that's kind of what happens. We didn't know a factoring method to come up with that, but we used the rational roots theorem to at least get it to a quadratic that we could deal with. And we eventually found our solutions. Now, let me ask you this. If I would have come up with a third degree polynomial, what would I have to do then? Start over. Yeah, if you look at the process map, it does tell you that if the degree of the polynomial is not 2, if it's greater than 2, then you got to start over and start plugging in your p's and your q's again. Now, it may seem like a lot of work, but just think about it. If we wouldn't have this idea of the rational roots theorem, we would have no way to even start. But because we have a rational roots theorem, we have an idea of a good guess. We guessed a negative 1. It worked, and so we were on our way. Okay? All right, you kind of see the background. Let's try rolling through a second one, then you could try a few on your own. I start with identifying the number of roots. How many roots are there? Does it factor? No, so I must use the rational roots theorem. I first identify my p's and my q's. What are my p's? 1, 2, and 4. Those are factors of the constant at the end. The q's are the factors of the lead coefficient. What are factors of the lead coefficient? 1. You take your p's, you divide them by your q's, and write them as plus or minus. So we have plus or minus 1, plus or minus 2, and plus or minus 4. Again, I always like to start by plugging in 1. I think it's the easiest one to work with. After we've identified our possibilities for our p's and q's, again, it says use synthetic substitution to find one of the roots. Then divide it, and then try to solve from there. So we'll go through that process. Here we go. Does 1 work? Yes. 1 to the third plus 3 times 1 squared minus 4 is equal to 0. So 1 is one of my solutions. What do I do then? I divide 1 into the polynomial. Drop the 1, multiply. I get 1, add, I get 4, multiply, I get 4, add, I get 4, multiply, I get 4, add, I get 0. What is my resulting polynomial? Does that factor? Thank you. What does it factor to? X plus 2 times x plus 2. So what are my other two solutions? -2 and -2. And my original solution was 1. So my three solutions are 1, -2, and -2. And now we found all three. Any questions on example 1 or 2? Okay, what I'd like you to do is take about 5-10 minutes. I'd like you to try examples, try problems 3 and 4, and see where we get there. Okay? If you get a remainder, you did something wrong. So a couple questions, you guys, that we need to address. First of all, if you get a remainder, you did something wrong because it's supposed to divide evenly. Second of all, you do need to list the options because on the test, part of the points you'll be given is that you can find all the options. And third of all, I want you to flip the page over no matter where you're at. I want to show you a couple examples on the back side and help you think through this just a little bit here. I want to show you why this works. A lot of people say it seems kind of like magic that you could just pick those numbers. It's not really magic. Watch how this works. Let's say we had 2x squared plus 11x plus 5 equals 0. Does that factor? It does. In fact, I have 2 and 1. I have 5 and 1. And if I try to factor, I go 2x and x. And if I go plus 1 and plus 5, that is properly factored. So watch. What's the solution here? What's the root here? -1/2. What's the root here? -5/1. So look at this, you guys. My solutions, look at where they come from. -1 and -5 are on top. Those are my p's. 2 and 1 are on the bottom. Those are my q's. It's not by mistake that happens. That's the way that generally when we solve for them, we find out that they work. So I just want you to be aware that it works out like that. That it's not magic. If you flip over the back side, again we identify the number of roots: 2x to the third plus 9x squared, yada yada. You are going to have 3 roots. we have 3 solutions. But when you identify the p's and the q's this time, it's a little bit different. What are the p's? 1 and 3, what are the q's? So now you have more than one q. So when you look for the q's, or when you look for the p's over the q's, you have to divide each p by each q. So 1 divided by 1 is plus or minus 1, and then 1 divided by 2 is plus or minus 1/2. Then I move to my second p. 3 divided by 1 will be plus or minus 3, and 3 divided by 2 will be plus or minus 3/2. So those are your choices, and I want to make sure you can list your choices. It'll help you in the long run. So that's this example, okay? That'll help you work through these pieces. And finally, 7 and 8. What's different about 7 and 8 is that you have it to the 4th power. So when you first go through the process, you'll then come up with a 3rd degree polynomial, a cubic, and you'll have to start the process again. So for problems 7 and 8, you have to do it twice through. And notice I say at the beginning that these are some of the easier problems. That's because we haven't come up with any irrational solutions. Furthermore, we haven't come up with any imaginary solutions, and that's what we'll investigate tomorrow. So you have the rest of this time to work on this sheet, try to finish out the problems. Would you like to see the answers so you know whether or not you did it right? Okay, I will put that on the board for you so that you can see whether or not you did them correct. Actually, I think I have them all. Let's just write them down real quick here. It looks like 6, 7, and 8 are right there. 6 is 1, -1/3, and -4. 7 should be 1, 1, -2, and -3. And 8 should be 2, -2, -3, and -4. And 5 should be -3, -1, and -1/2. So those are your solutions. That way, at least you have a point to reference and to start from. So we will deal with more difficult problems tomorrow. Okay.